Now, some important things to note when you're evaluating the definite integral. You already know how to integrate a function one term at a time, so you can go ahead and do that. We've also learned how to find the primitive by reversing the chain rule, but we don't yet know how to reverse the product rule or the quotient rule. So if you see a function that looks quite complicated and it's got several functions of x multiplied together or divided, we need some other strategy. And the strategy would be that you might need to expand your brackets or take complicated looking fractions and make them into individual terms before you start to find their primitives. Let's look at a couple of examples of that. Now this function has got two parts. There's the x part and the x plus 1 part. They're multiplied together. We can't undo the product rule. So what we should do before we start is really just rewrite the question and change the look of it into something that we can work with. So expanding the brackets here, I can have x squared plus x, and now I can find the primitive of that one term at a time. So my first step is I write my square brackets. There's going to be two terms inside the brackets because there's two terms in my function. And then I find the primitive of this term, which I know to add 1 to the index and divide by the new index, and then just double check, does this differentiate to make that? Yes. And then with this one, if I integrate this, I just get x squared on 2, doing the exact same thing. Remember, this is notionally a 1 here, so I've added 1 to the power, divided by the new power, and then double check. When I differentiate this one, the 2 comes down, cancels out, just gives me x, so that's looking good. Then I write my bounds. I've got 6 and 1 here. Next step, I need to sub in the 6 to this whole thing, and then subtract the subbing in of 1. So I'm going to need to use round brackets for each part. I probably don't really need brackets for the first part, but I definitely do for the second part to avoid making that classic sign error. So subbing in 6 to this whole expression, I have 6 cubed over 3 plus 6 squared over 2. And then I need to subtract the whole thing, subbing in 1 this time for x. So I'll have 1 cubed, which is just 1 over 3, plus 1 squared, which is just 1 over 2. Now obviously some parts of this can be easily done in your head. I can see here that I've got 36 divided by 2 and I know that's 18. But if you've got a bunch of things to do here, the quickest thing is probably just to reach for your calculator. And being careful, of course, with your calculator, either use the brackets, or if you're not using the brackets on the calculator, make sure you allow this sign to affect this one. Now, my answer here has come out in a few different ways. I'm going to write down 89 and 1/6. I've used fractions instead of decimals because it's exact, faster to write, don't need to say what I've rounded it off to, and it's perfect. If you were to have it as an improper fraction and write something like this, it's not wrong, but it gives you less of a sense of just how big of a number this integral really is. So it's not wrong, but I think I prefer this one. Okay, this example looks pretty complicated, but what we need to do here is just tidy it up so that it's single terms that we can integrate, because we can't reverse the quotient rule. Now you'll notice that our bounds are negative. That's okay, we can sub negative numbers in. Let's see how we go. Now first step, let's just rewrite the question, tidying it up. We can split this fraction up into x cubed over x cubed. Now you could do that and then go, oh, that's 1, and change that on the next line, or you could spot that already in your head. Let's just do the whole working this time. And as you get better at it, there's certain lines that you might leave out. Next we can subtract 2x to the power of 4 over x cubed. And we're going to integrate then that whole thing. This is our new version of the function. So on the next line, I'm going to continue just to tidy it up because I've got a bit of cancelling I can do here. I can see that this is 1, and here I can divide by x cubed, top and bottom, and I have minus 2x. That's now made our lives a whole lot easier. Now we're ready to draw up our square brackets and put in the primitive of each part. The primitive of 1 is just x, and the primitive of 2x is x squared, so I need to put minus x squared. At this point, differentiate these terms one at a time and just double check that it does give you these. 1 minus 2x. Yep, I'm good. Now I can put my bounds in, minus 2 and minus 3, and I'm ready for the substitution step. So first thing to do is substitute minus 2 in for x. So I need minus 2 minus minus 2 squared. Now notice here, there's a chance to mess up your signs. So literally just rewriting what you have, but putting in brackets what you're subbing in will prevent that mistake. It might take an extra line of working, but it's going to stop those mistakes creeping in. Next, we want to subtract this whole thing, but with the -3 subbed in. So I'm going to use big brackets for that whole section to make sure I don't make a classic sign error there. So first thing, I need a -3 there, and then I need to subtract -3 squared. Now it's up to you, however you prefer to work. Some people might reach for their calculator at this stage and put that whole thing in, brackets and all. I prefer to just tidy it up. I think I can do more in my head here a little bit quicker than with my calculator. If I square -2, I get 4. So I'm subtracting 4. And here, if I'm expanding my brackets out, in fact, no, let's just keep the brackets for this stage. I've got -3, and I'll tidy up this part. If I square -3, I've got 9. So I'm subtracting 9. So now I've got -2 minus 4. Well, that gives me -6. And then I'm subtracting -3 minus 9. That's -12. So subtracting a negative is like adding, and I can see there without actually reaching for my calculator later that I've got 6. Now I find that mental arithmetic probably a little bit faster, but depending on the numbers, you might have reached for your calculator way back here. And a couple more things to note. Just as when we're differentiating, we don't like to differentiate terms in x when they're in the denominator, we instead change them to negative indices. We need to do the same thing when we're integrating. So a question like this, where we've got 1 over x squared as our function, we want to start by rewriting the question to look a little bit easier like this. Now we can go ahead and complete all of our steps. We've got our square brackets, we add 1 to the index number, and we divide by the new index. Now that means divide by -1. That's the same as just putting a negative out the front. So you can put it out the front or down the bottom, makes no difference. Double check that when you actually differentiate this, you get this. Bringing your -1 down the front would cancel with this negative to make a positive, and you'd reduce that -1 to -2. So it looks right. Then put your bounds in, we've got 5 and 1. Then do your subbing in step, so we're subbing in here -5 to the power of -1 minus -1 to the power of -1. Now there's a lot of negatives in there. Your calculator will sort this out nice and easily for you, or you might prefer to do it by hand. This really, 5 to the power of -1, that's a fifth, isn't it? So we've got -1/5. Minusing a negative is just adding, and 1 to the power of -1, well that's just 1 over 1. It's just 1, isn't it? So effectively 1 minus 1/5, this gives us 4/5. And I can actually do that surprisingly easily without the calculator. Similarly, we don't differentiate surds. Instead, we change them to fractional indices. So we need to do the same when we're integrating. So the first step of this question is to rewrite it so that it's able to be done like this. Second step, we use our square brackets to find the primitive here. Now add 1 to the index, that gives us not half, but 3 over 2. And then we need to divide by the new index. Now remember that dividing by 3 over 2 is the same as multiplying by 2 over 3. And it's easier to do it that way because it will look tidier. I can multiply by 2 and divide by 3 and write it like that. Then I put in my bounds. Next step, I'll just continue across here. Normally I'd go down, but I'm running out of space. Sub in the 2. So we have 2 lots of 2 to the power of 3 on 2 over 3. And then we need to subtract the subbing in of when we sub in 1. Now 1 to the power of anything is going to be 1. So we're going to have 2 lots of 1 over 3. That's just 2/3. Now this looks a bit nasty to do in our head, so let's reach for our calculator now. And here it's kind of unavoidable that we're going to need to round off our answer. So we've got 1.2189. I'm just going to round it off to 2 decimal places and then put to 2 dp. Now the other thing that we need to remember is that we can't ever integrate across a vertical asymptote. Why not? Well, we've looked at the fact that when we're integrating, we're finding a sum of values. So if we've got something like, let's have a look at a function like this. We've got a hyperbola where we've got an asymptote here along the x and the y axis. If we were going to try and find, say, 2 over x dx, and we're looking at a boundary from 0 to 1, then we're actually finding a sum of values of this space in here. And it goes onwards and upwards forever, so it can't actually be bounded. It doesn't have a proper boundary. So we can't find a definite integral of something that doesn't have definite borders.